I told you that in my previous class, for few more classes, we are going to see about the instructions and assembly level programming. In the previous class, we have seen move instruction, and also we have seen one example or one or two examples on move instructions. We have seen one example uh, moving or swapping data from one memory location to another memory location, swapping a word from one memory location to another memory location, and also we have seen swapping a block of memory from one block of memory location to the other block of memory location. So we have seen all these things. We have seen different types of move instructions. We have seen one instruction called as increment instruction. We have seen how to increment the data in registers. We have also seen how to increment the data in memory. So memory offset address can be referring to a byte, or it can be referring to a word, or it can be referring to a double word, right? So whenever you increment a byte from the memory, it is mandatory that you say it is increment byte pointer, and then you just mention the offset address. It can be direct or indirect, right? Similarly, whenever you read or write a word, then it is mandatory to keep increment word pointer or increment or decrement word pointers. This is very important. You need to remember this. This is an example we have seen, increment byte pointer. Okay, you see what is a memory location. You see its corresponding physical memory, and also the segment address and the offset address, right? This concept always you need to remember, right? Physically, the data is stored in the memory using 20-bit address, but when we refer to that particular physical address, we always use this segment register and the offset register. So here you see the offset is in the BX register. The offset address is in the BX register, right? That is 4000H, and data segment, right? Segment address, always data will be stored in the data segment in the segment address 2000H, right? So when you increment the entire byte, only byte will be incremented. When you just put as a word, only word will be incremented. So we have seen all these things, and also we have seen a program, okay, where you will have to, okay, copy a 50 byte, a block of 50 bytes of data from a memory location 42000H to 44000H, right? Okay, assume that both the memory blocks are in the same segment. Assuming that both the memories are in the same segment, what you have been given is a physical address. Physical address of the first block of memory is given as 4200. Similarly, physical address of the second block is given as 4400H. This is what we have seen in our previous class, right? So now if you take this, the segment address, if you take the segment address as 4000H, okay, and offset address for this it will be 2000H. Similarly, for this, I told you that it is in the same segment, so segment address will remain the same 4000H. Okay, and also offset address is going to be 4000H. You can check the physical address from this segment address and offset address. You're going to get this. Similarly, you're going to get this, right? So as usual, you need to tell this information to the microprocessor, right? So you put this segment address into the DS register first. Okay. After that, you put this offset addresses into this certain index registers, right? And then try to copy this data into a register in a temporary register AL. Okay. And then you can point this to, okay, we can point this to, say, SI, put it in the SI. So in the bracket, it indicates the data at that offset address. Similarly, you can put this into the DI register. The DI is the pointer for this. Okay. Similarly, SI is the pointer for this. Now using this pointer, try to put this data first into AL register. Then from AL register, you copy into this offset address. That is the best program you can do for this. You cannot directly put this into this memory location. There is no move instruction which transfers a data from one memory location to the another memory location. So you will have to transfer first to the AL register and then to the another destination. This is what you have to do. This program we have seen in our last class. This is what your segment address and the offset address. Now you just have to write a program for this. Okay, so program is very simple. I have written the program in my last class, right? Using loop statement. So I don't want to repeat it again now. So hope you all have seen that program and you have practiced it. Now, let us see about something called as assembler directives. What is this assembler directives? It's very important to know from the programming point of view, what is this assembler directive? Listen carefully. In the programming part, you have actually two sections. One is data section, another one is the code section, right? Normally, when you write a program, you use data, and then you try to declare the data sets here. You try to put the data sets here, right? Then you write code. Then you write all the codes here. So this is your data part, and this is your code part. Now, in the data part, whatever you enter in the data part, those are stored in the data segment of your memory. Those are stored in the data segment of your memory, right? Ultimately, everything is stored in the memory itself. So this code part, this is stored in the code segment part of the memory. Now, when you declare the data in the data part, in the data segment part, okay, after data, right? How those data are stored in the memory. That is what we are going to see. See, outside, ultimately, this is going to be stored in the memory. This also stored in the memory. So these are nothing but your assembly codes. I have told you in my previous class that these assembly codes are converted into machine code, and these machine codes are stored. These are nothing but a hexadecimal code. You already done the conversion, you know it. So this is stored in the code segment part. Ultimately, what is stored is a hexadecimal number. Whether it is a data, whether it is a code, both are stored in the memory, right? Now, this assembler directives, what it does? This assembler directives will direct the assembler, okay, to do certain task. For example, dot data is also assembler directive. Dot model is also assembler directive. Those are all not part of the assembly code. You must have done some coding part now, right? You've written the program. Already 3 labs are over. Now, you must have seen there is dot data, right? There is dot code, dot model, dot stack. All those are nothing but part of the assembler directives, right? Okay. So what is that something, assembler directives, and what is that, data part which you are going to use in your program? See, data declaration. Let us start from the data declaration. Right. You must have already seen that you declare the data as a DB, DW, and DD. In C programming, you normally declare your data as integer, float, right? And so on. In a similar way, in the assembly programming, if you're dealing with a byte, you use DB. If you're dealing with a word, you use DW. If you're dealing with double word, that is 32-bit data, then you use DD. Right? Every data declaration in dot data part, okay? Suppose here I'm going to declare 3 data. Data 1, data 2, and data 3. Right? So I'm going to declare data 1 as DB. Right? Now you see here, say I'm going to initialize the data 45H, 35H, and 74H. This is going to store the data 45H, 35H, 74H. See, these are all hexadecimal data. These are all hexadecimal data, right? So your microprocessor keeps every data as a hexadecimal data. Suppose you keep comma here, right? Now you put only 50. You don't put H. You don't put H. So what is microprocessor doing? Microprocessor is taking this data as a decimal data. It will convert it into hexadecimal, and that hexadecimal data is stored in the memory location. Have you understood this? This is very important for you to know. If you don't put H here, it will store its hexadecimal equivalent in the memory. If you put H here, it will put the 50H, that is hexadecimal data. This is the declaration of a byte, right? And you declare DB here and try to give 16-bit value, it will give an error. Your compiler will give an error. Similarly, data 2, which is word, which is 16-bit, is declared like this. See, now can you see here it is declared at 37H, right? In that case, what it will do? It will just take this as a 00, right? Understood this? This is 16-bit only, right? It is 00. Okay. Now, double word means 32-bit. Double word, see, double word, 2 words are there. Okay, it is declared like this. Okay. Now, see, these data supposed to be stored in the memory in a continuous memory location. Okay. You understood this? These data are stored in the memory in a contiguous memory location. That means microprocessor considers it as a stored from a continuous offset address. See, when I say continuous memory location, physically it is 20-bit address only. But microprocessor, we are saying it as an offset address, 16-bit offset address. That's why that 16-bit offset address can be anything, right? From 0000 to FFF. You all know that offset address can range from 000H, is hexadecimal address, to FFFH in any with respect to any segment address. You all know about it. Segment address. Right. So this, for example, data segment. If I take a data segment, right? Data segment, there will be segment address, right? Segment address is also varies from 00000 to FFFF. H. That means whenever a data is declared, it is saved in data segment with this particular segment address. We have already seen it. And under that segment address, there are offset addresses which are starting from 0000 to FFFFH. So totally you can save in one segment address 64 kilobytes of data whenever a memory is byte addressable. This is what you need to always remember. Now, between this 0000 to FFFFH, where to start, right? From which address, which offset address you can start storing the data. That can be controlled using an instruction called ORG. What ORG does it, right? So the syntax of ORG is ORG some 16-bit value, right? So this is the instruction which is first actually written before the data declaration, right? So now what I do is I will just write ORG 0000, which indicates that whatever data you declare after this, it is stored from the offset address 000H, right? Okay, and it is stored from that point in a continuous location, Okay, now let us see how it is stored in memory, okay, for this particular example, right? Can you see here? This example? Let us see this example, right? Let us see this example. See, try to understand this. In the quiz, you may get any, or in the midsem, you can get some, questions on this. It's very simple. It's very simple to understand. ORG 0000H, right? Now, this is coming in dot data. Since it is coming under dot data, that means all these are nothing but your data, which will be stored in some segment address in data segment. Remember that, okay? And you know, once I said that it is stored in some segment address, and under the segment address, you have offset address, right? Which starts from 0000 to FFFFH. Okay, I'm choosing my data, or this data has to be stored from the offset address 00000. Okay, now see, data 1 type db, it's of type byte. I'm declaring it as 25. See, there is no h over there. Okay, just check. Data 2 is db and declaring in the form of a binary format. See, binary format, right? Okay, and then data 3 is going to be of db. Now this is 12h. After that, see here, after that I'm changing my offset address. My offset address I'm changing to 0010h. I'm not continuously putting indents. Okay, so your data 4 is again db 2591h. Okay, now just check this. db, it is 2591h. See here, it is db, it's written as db, right? What is the 2591h? It is actually, you know, array of numbers, right? Okay, so you just have to know about it. Okay, now let us see. Once again you see this, right? Once again you see this. ORG is changed. It is 0018. Then it is db. Now check this number. There is no h here, and it is actually written as a some characters, right? Okay, so you just have to see that. Just let us see how it is stored in the memory. Right? Let us check this. Now see this. Starting from ORG, see how it is stored in the memory. Assume this is the memory. This is the memory. This is going to be our offset address This is going to be offset address. Okay, and you have this table. This is the offset address. This is offset address. This is offset address. This is offset address. Okay, this is stored in the data segment. It's stored in the data segment, and it is stored, okay, in some segment address. Okay, let us not worry about the segment address, in some segment address, right? See, now starting from the offset address 00, it starts storing the value. First, it is storing 19H. How come 19H? Can you see 19H? How come 19H here? You all know, I told you, right? I told you that 19H is, that is hexadecimal part of the this 25. 19H will come here. Now next offset address. See, your next data declaration is this. This will go to the next add. So this will store in the offset address 0000. Okay. Now the next data will be stored in 0001. Okay. What is this? It is declared in the binary form, but it is actually, this is 8, this is 9, 8, 9. So this is 8, 9 in hexadecimal. You can see 8, 9 is stored here. So next location you have this data 3. Okay, and it is 12H, 12H. So that 12H is stored here. Understood? After that, the data 4 is stored in different offset address, because once again you are actually using org 0010, right? And what is this? This is actually, if you have it between this single code and these numbers, these are like nothing but stored in the form of its ASCII value. Right, now you see 2591. Okay, say within the single code, if you put 2591, 2 is a character, 5 is a character, 9 is a character, 1 is a character. When it is stored in the memory, it is storing its equivalent ASCII value. Right? Now, what is the ASCII value of 2? See, starting from the address 0010, starting from the address 0010, first it will store the ASCII value of 2. The ASCII value of 2 is actually 32H. Similarly, this is the character. Just remember the character. So ASCII value of character 5 is 35. Similarly, ASCII value of this is 39. ASCII value of this is 31. Have you understood this? Okay, 31, which you can see here. Right? Okay. So this is what actually the data is stored in the memory. Right? You understood this? See, from 0010, the first character ASCII value. After that, next ASCII value of this, ASCII value of this, ASCII value 31. ASCII value. Okay. After that, once again you are calling 0018. Since you're calling 0018 again, okay, one more data declared here. One more data declared from 0018. See, 0018, one more data is declared. Now, what is the data? Data 5. Okay, its variable name is data 5. It is of type DB and question mark. It's a question mark. That means we don't know the data. You're going to store it once you calculate the data. In such cases, whenever there's a question mark here, it will initialize it with the 00. It will initialize it with the 00. You can see here. This is the way the data is stored in the memory whenever you declare data in the program. Right? And remember that it is stored in some data segment with the data segment address, with these offset address. Okay, for this example, this is what actually the way data is stored. You should remember this, how the data is stored. Right? Okay. Now we will have a couple of examples here. Okay, just go through this. I think you will very well write, okay, how the data is stored. See, normally in the examination, what will happen is you will be given this you will be given this. You have to convert this into this table. It's very easy. Okay. So these are the data part. These are the data part. Right? These are the data part. All of you know about it. So from where this data will be saved in the memory from the offset address 000. Okay. And I told you message to DB, it is a array of character. It is a array of character. It's a string, right? So within single quote or double quote, if you see, this is an array of characters. Now, what is stored in the memory? Starting from 0000H, ASCII value of this, then ASCII value of this, ASCII value of this, ASCII value of this, ASCII value of this, ASCII value of this. Can you see here? 31, 32, 33, 34, 35, 36. These are the 4 corresponding to this. Understood this? Okay. Then message 3. What is message 3? Message 3, you can see it is nothing but DW. It is a 16-bit value, right? So after this number is stored. So first it will store the lower byte, then it will store the upper byte. See, 67 is stored first, and then 66 is stored. And then in the continuous memory location, I have not changed my ORG anywhere. Okay, so if at all between ORG is there, the offset address will change. Okay, now next data 1. Okay, data 1 is 1, 2, 3. Can you see 1, 2, 3? There is no H. It's same, right? Hexadecimal from 0 to 9 is the same as the decimal value, right? So after that, this 1 will be stored, then 2 will be stored, then 3 will be stored. After that, see, it's a character. After that, character A, the ASCII value, equivalent ASCII value of character A, it is small a, is stored in the next location. See how this continuous location data is stored. Now, see here, this is actually F0, right? This is F, this is 0. So F0 is stored in the next location. Next, data 2. Okay. Now see here, it is DW, okay. 12 and 13. No H is given there. Is there any H given there? No H given there, right? Okay. Now, since there is no H given there, can you tell me what is that value? After F0, it is DW. Is the 6? This is a 16-bit value. This is another 16-bit value. What is stored? Actually, it is 0012, right? H is not there. Then tell me what is stored. Instead of 0012, what is stored? If you convert this 16-bit value into the hexadecimal, it is 000C, right? 000C, right? This is 0012 is C value. So hexadecimal equivalent is 000C. So in such case, after the F0, after this location, F0 is stored, okay, the lower byte of this 12, that is 0C, is stored. Then upper byte, that is 00, upper byte 00 is stored. Similarly, next is this 13 is stored, and 13 is now here declared as a DW. Since 13 is declared as DW, it is actually 0013 in decimal, right? In hexadecimal, this will be 000C, because 13 is 0C. I understood this. Okay, so to be very careful that this is 0D. Sorry, 13 is D. So 000D. So in that case, the lower byte 0D will be stored first, and upper byte will come next in the location 0010. I understood this, how the data is stored. Okay, then DW 2345. So in the next location in 0011, 45 will come first. 45 will come first, lower byte, then upper byte 23 will come next. See. Right? Next, double word 32-bit. This is double word 32-bit. Actually, what is given here is only 300H, but you have to actually append zeros How many zeros you have to append? You have to make it 0000, 32-bit. The 16 plus 16. This will be 000300H. Actually, this is the data, right? Double word DD. Okay. So what is shown here is 300H, but actually data is 00000. Totally it is 32-bit data, right? Totally it is 32-bit data. So how it is stored? First lowermost byte. Okay. So after 23, lowermost byte 03 is stored. 00 is stored. Next byte is 03. Okay. 03. Next 00. Next 00. This is the way it is stored. After that, see here, after that, it is DB 9 DUP. Okay. After that, it is DUP. You can see here DB 9 DUP FFH. What exactly it means? See, the data you are going to use is of type byte. 9 DUP means you have to duplicate 9 location with the value FFH from this memory location. The last memory location yours is this 0016, and from this location, okay, you're going to save FF in the 9 location. That's what the declaration is. DB 9 DUP FFH. That means you are going to save FF 9 times in the 9 continuous location. Okay. So this is the way the data is stored in the memory. All of you understood now how the data is stored in the continuous memory. Okay. Now, suppose I will give you one question. Suppose if I change my ORG, somewhere I'll put ORG. Okay. Somewhere I'll put ORG here. 4000H. Now, can you tell me where I should change, okay, my address here? Where I should change my address? Come on. Can somebody tell me? I have to change some offset address here. Where I should change? I have included ORG 400H here. Including ORG 400H means all this data after this will be stored from the location, from the offset address 400H. Right. Okay, now tell me, in this table where I should change? Can somebody unmute yourself and can tell me the answer? Where I should change? Come on. Hope you're all active, not sleeping. You can put it in your WhatsApp group. I want you to be little interactive. Where I should change? Tell me. Come on. Don't worry about the war. Let us concentrate on our, okay, yes, 000D, right? So this will change to 4000H. After that, it will be 4001, 40002, and so on. Right? Okay. So hope all of you understood this. This is very, 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 very important. Fine. Okay. So we'll proceed to the next. I have told you about this. Once again, you can see how the data is stored. See. Right? Okay. Now, there are some EQ EQU directives. EQU directives. What is this EQU directives? See, this is very important. You must have seen that constant, right? Constant declaration in C programming, right? Okay, or something called as preprocessor directive. Preprocessor directive. It doesn't store in the memory, right? So in 8086 assembly programming also, you know that something declared with the EQU, something declared with the EQU, okay, this data is not stored in the memory. It will not stored in the memory. Instead, wherever you come across with count in the program, right, it will replace this count with the 10. That's all. That's all. Right? Here also, a constant is declared as EQU with a value 20. Right? Somewhere in the program, here, like you see here, okay, like you see here, constant and count is coming in the program. Now, what will happen during execution, that this count will be replaced by 10 and this constant will be replaced by 20, right? But it will never be stored in the memory. It will be never be stored in the memory. So what happens with this program now? Tell me, right? Now this AH register will have a 10, value 10, and AL register will have value 20, and 10 and 20 will be added, and your AH register will have the addition of 10 and 20, which is going to be 30H. Right? So this is what the importance of EQU is. Okay, what you need to remember is it won't be stored in the memory. All this EQU, whichever EQU is declared here, it will not go to the memory. Will not go to the memory. It doesn't require any offset address. When I said that it is not going into memory, okay, it doesn't require any offset address. It will not go to the memory. Hope all of you listening there to this. These things will not be again covered in the class. Okay, this is the regular class only. Okay, so now can you write this as an offset address table? Right? Can you write the offset address table? See that these two will not go to the memory. The data will be start storing from 0010H is 45. Right? As I told you, EQ will not go to the memory. This also will not go to the memory. Right? Wherever EQ is there, it won't get into the memory. You can see that now. See here. Right? These two will not go to the memory. See here. Even though your data offset address starts from here, it will start storing 45 from here. Okay. See how the data is stored in a contiguous memory location using the offset address. Just look into this. Look into this. See, after that 10H. See, this 10H is actually 0010. Okay. Now, then see the next address 10H is stored. Then upper byte 00 is stored. And here also you can see after that this 00 will come. Then this 35 will come. Right. So there's a continued location. You can see after. See, this is DD. DD means it is 000. Okay. So after it stores this 09. Okay, in this location, okay, it will store 02. See here, 02. Then it will store 09. Then it will store next byte. Then it will store next byte. Right? After that, this value 2 is not stored in the memory. Can you see this 32, which is not coming in the memory? Not coming. Then data 3 is stored. So this is the way the data is stored in the memory. Right? Okay. Understood this? Now see here, ORG is value 2. Right? What is value 2? Value 2 is EQ. Okay. Then what is the address? This value is nothing but 0032H. So this will start from 0032H. Can you see here? See, from 0032H, you have 10 continuous location, which is initialized with a question mark. Okay, and then comes another 32-bit value. Okay, double word, and this one. That is 04, 03, 02, 01 stored one by one here. Hope all of you understood this, how the data is stored in the memory. Now, for this program, I have a program here. Okay, I have a program here. You have to give me the answer now. Now you have to tell me the content of the respective registers in this. Okay, you have to tell me the content of the respective registers using this, using his. Right here you have data 1, data 2, data 3, everything is there, right? Right, data 1, data 2, data 3, everything is there in this. Now you have to tell me the content of the registers. Right, all of you take a pen and paper and just do this work. Move SI comma DAT3. See, this DAT3 is the memory location. DAT3 is the memory location. SI is the 16-bit register. You know that. SI is the 16-bit register. So what this instruction does, it will copy 16-bit content, okay, from the offset address DAT3, from the offset address DAT3 to the SI register. So you have to find out now what is going to the SI register. Right, now let us see what is DAT3. All of you do this. What is DAT3? See, DAT3 is here. Right, DAT3 is here. So what is there in DAT3? See here, DAT3 is pointing here now. DAT3 is pointing here now. Okay, now what is the instruction? Instruction is move SI comma DAT3, this DAT3. Right, so what happens? This is the offset address. From this address, data has to be loaded. Now, what will be loaded into SI? What is loaded into SI is, first it will, this is a 16-bit. Okay, first it will load the lower byte. The lower byte of SI register, first it will be 00. Upper byte is also 00. I've understood now. This is 16-bit transfer. Since it is copying 16-bit data to SI register in this, it will copy from the two locations, right? From the first location, it will copy the lower byte, and then it will copy the upper byte. All of you understood this, right? Now tell me, what is the value of the SI register now? I'll go back to here. What is the value of SI register? Come on. Somebody can unmute and you can just tell the answer. 000H. So SI register is holding now 0000H. Right? Now, listen carefully here. Move AL, listen carefully. Move AL, DAT1 plus 1. Move AL, DAT1 plus 1. Can you tell me what is transferred is the 8-bit data. So 8-bit data is transferred or copied. 8-bit data is copied from the memory. Which location? Which location? From DAT1 plus 1. From DAT1 plus 1. Now what is DAT1? What is DAT1? Let us see here. What is DAT1? DAT1 is this one, right? DAT1 is this one. So DAT1, what is DAT1 location? DAT1 location is 0010. Is it copying from that location? No, it is copying from plus 1. Plus 1. That means an 8-bit data is copied from the location dat1 plus 1, okay, to the AL register. So what is there? What is the data available in this location? The data available in the location is, okay, it is actually the not data. You don't have the square bracket kept there, right? Okay. So what is transferred is, okay, in this case is the data, right? I've understood this now. The data is transferred, okay, from this dat1 plus 1. Okay, the data transferred from dat1 plus 1 to the AL register. What is the data transferred? 67H. Yes or no? Hope all of you understood. No confusion here, right? Dat1 plus 1. So I will just go back to this. Okay. Now in this case, what is there in the AL register? Come on, tell me. 67 there is there in the AL register. Hope all of you are understanding this. Okay. Now see here. It is dat1 plus 4. How much data is going? 16-bit data. BX is a 16-bit register. Okay. Dat1 plus 4. Let us see. Go back here. Dat1 plus 4. Where is dat1? This is dat1, right? Now dat1 plus 4. Okay. 1, 2, 3, 4. Okay. Dat1 plus 1. Dat1 plus 2, 3, 4. This is the location. Right? This is your location now. Dat1 plus 4. This data will go to the BX register. This is what you have. Move BX comma dat1 plus 4. Now, what is there in dat1 plus 4? It is 16-bit. This is the lower byte. This is the upper byte. So what is transferred in the BX register is 0010. This is stored in BL register. This is the lower byte, and this is the upper byte is stored in the BH register. Totally, your BX register will have 0010. Understood this? Now I will go back to this. What is there in the BX register? 0010H. Right? Now tell me, what will be there in the BX register now? Add BX 20H. Right? Now tell me, what will be the content of BX register? Come on, you can unmute and tell me the answer. Na? All these are very important from the examination point of view also. Right? See, what is there in BX register? Already in BX register 0010 is there, right? You plus add 20H to this, you get 0030H. 0030H. Okay. Now, next, what is the content of AL register? Question is, what is the content of AL register here? See here, what it does. This is copying the data from the memory, right? See, this is the source, this is the destination. It is copying the data from memory to the register. It is copying data from memory to the register, you know. Right. Now, from where memory? From some offset address. Where is the offset address? Offset address is available in BX. Right? BX register. What is the content of BX register? Now tell me. What is the content of BX register? The content of BX register is 0010H. So it is actually copying the data. It is copying an 8-bit data from a memory location 0010 to the AL register. Now tell me, what is there in the memory location 0010? Now see here, come back to this. What is there in memory location 0010? 45, right? Memory location 001045 is there. Okay. Okay, now, okay, I think there is a mistake. Let us see. BX is not 0010. BX is 0030. I'm sorry, because we added 20 in this. Okay. BX is 0030. BX is not 0010. Just make a correction, right? Because here BX is added with the 20 and it has become 0030. And we are using that as an index for indirect addressing mode. So that means in this instruction, data is copied from 0030. So let us go back and see what is there in the 0010. 0030. Let us check. Okay, 0030, right? Okay, 0030. Now we don't have 0030. We have here. See, 56 is there, 56H is there, right? Okay, so 0030 location data is copied. Okay, in this case, what is the content of AL register? 56, right? Okay, now you see what is copied to, what is the content of BX register in this? What is the content of BX register? DAT4, right? Now what is that data for DAT4? It is copying. Listen here. DAT4 is a memory location. Okay, it is copying. It is copying. See, this is LEA. I will tell you. LEA. I will tell you about LEA. LEA is a instruction to load the effective address. Here it won't load the data. This is not move instruction. Try to understand this. LEA, suppose if I say LEA BX, comma, DAT4. See, this LEA means load effective address. Now what it does? What's the difference of this LEA and move? In move, it will actually it will copy the data from that address. But in this case, it will load the BX register with the address of data 4. That means with the offset address of data 4. Remember carefully. In this case, it is not loading the data. It is loading the offset address. Now, tell me, from the previous list, what is the offset address of DAT4? Where is DAT4? Right? Where is DAT4? Check here. DAT4. What is the offset address of DAT4? Offset address of DAT4 is 0030. Right? Offset address of DAT4 is 0030. In that case, now what is the value which is stored in the BX register? Address of this, that is 0030. That is what the function of this load effective address. You understood? In move instruction, what it does, suppose in move instruction, if I say DAT4, now tell me, what is the content of BX register now? The data, a 16-bit data from DAT4. Now, what is the 16-bit data from DAT4? Okay, this one, right? Data is this one. Some data, that will be some data over here. If it's junk, it will be junk. This is the lower byte, this is the upper byte. Okay, this is stored in the BX register if it is a move instruction. If it is a move instruction. In load effective address, it will actually store the address of this DAT4. This is the difference. Okay, so now I will leave other things to you, right? And also I will tell you this offset. Offset is also something similar. Okay, right? Now, what is this move BX offset DAT4? I'll tell you. This and this does same thing. Okay, this will move the offset address of DAT4 to the BX register. The same instruction is written as load effective address BX comma DAT4. This also will load the offset address into BX register. So these two does the same thing. You just have to remember this. Okay, fine. Okay, So now just see what is loaded into AL register, right? Now this one also will load the data from the location DAT4, right? This also will actually load the same data. What is there in BX now? BX is you are having the offset address of DAT4. So AL register will have the same value here, same value here. It will be overwritten on the registers. Okay, here you can see this. Whenever there is a move instruction, it just copies. When it copies any data into register, old data will go, it will overwrite with the new data. Always you remember that. Okay, so when this type of question comes, you will have to write these answers. Okay, as what is the content of AL register and what is the content of BX register. Okay, these things you are supposed to do. Okay, so it will be something like this. So you will be given this. You will be given this. Okay, how the question will come. I'm trying to explain how the question will come. You will be given this. You have to get this table. It's very easy. And after that, you will be given this type of code. And you'll be writing what is the content of SI in this. What is the content of AL in this? What is the content of BX register in this? What is the content of BX register in this? What is the content of AL register in this? What is the content of BX register in this? Okay, you all get from that particular table. Okay, what is the content of AL register in this? What is the content of BX register in this during this execution? What is the content of AL register in this execution? What is the content of BX register in this execution? What is the content of AL register in this execution? What is the content of AL register in this execution? These answers, if all are correct for you, then you will get full marks. Okay, keep it in mind. You make this particular topic perfect. Okay, then definitely you will be able to score some marks on this. Okay, have you understood? Hope all of you understood about this, right? Okay, so we'll proceed to the next. Okay, dot models. Hope you have seen that you have used dot model small, dot model tiny, right? Dot model large. Normally you have used dot model small in your case. Yes or no? Right? So there are many models available in the TASM. What is this model? I will tell you. So all this theory I don't like to read, but I'll tell you actual concept. What is this dot model tiny, dot model small, dot model large, and all? Right? Okay. Now see here. You have this, segments, data segment, right? Segments. Each segment is of size 64K. All of you know about it, right? Suppose if I take the segment address as 400H, okay, this will have offset addresses starting from 000H to FFF. If you take total, this is 64 kilobytes of memory. Right. Okay. Now let us see what is model tiny. Tiny model requires that all program and data fit into 164K segment. See, then you can ask me, sir, why there is a separate data segment and code segment? Right? I've understood this. Why there is a separate code segment? So in this tiny model, okay, it will see that of course, segments are different, right? But it will see that your both code and data will reside within the 64 kilobyte of memory range. It cannot go beyond 64 kilobyte range. Understood this? The small models. Okay, your both code and data will fit within 64 segments. Right? Okay, so that is what the model tiny is. Okay, all of you know about dot code, know about dot data. What is this dot startup? Dot startup. See, you have something in the program. you must not have used this dot startup, but what dot startup does? See, always you use dot code, and after that you use something like move a x comma at data, right? Then move ds comma ax. All these things you use, right? See, instead of that, you can just use dot startup. Okay, so when you use dot startup, this is not required. That's what dot startup is. Okay, dot exit is exiting the program. Moment you put dot exit in the program, that means it will exit. It is actually using some interrupts to exit, come out of the program. All these are nothing but assembler directives. These are all not part of assembly instructions. This is something controlled by the assembler itself. That's why it's called as assembler directives. Okay, just remember this. It is called as assembler directives. Okay, all these things are used in the programming. For example, you see this program. You see this program. Can you just check what this program does? What this program does? It does simple move operation, right? Model tiny. Then you have dot data. Model tiny. Then you have dot data. Data 1 declared as 23. H is not there. That means it will go as its equivalent hexadecimal value. Then you have data 2, right? Then you have data 3, right? So it has become ulta in this, right? Okay, just you can see that this thing comes first and then your data comes next. But actual syntax, you all know how exactly it works, right? Then dot code, dot startup, right? In dot startup, you can see that you don't have that move ds comma at the rate data, move ax comma at the rate data, move ds comma x is not there. Directly you can write it, right? What this data does, program does a simple move instruction. Move bx comma data a2, cx comma data a3, right? Okay, so now what question may be asked in this particular question is that what is the content of the bx register, right? Okay, now what is the content of a bx register? Now tell me, can you tell me what is the content of bx register now? Come on, you can unmute and tell me the answer now. It is very simple. What is there? Data 2, right?
999.
999H is there. What is there in cx register? Also 9999H. What is there in the memory location data 1, right?
99.
Exactly. So it is 99, exactly 99. Okay, so data 1, it is actually 23 will be there in the DL register. Okay, like this you all know about this. Okay, so now you see move di comma 0002. Can you tell me 0002 is there in the di, right? Can you tell me what is the content of AX register here? Array of di. This is array of 0, array of 1, array of 2, 3, 4. This data you have put into di register. Now tell me what will be there in AX register now? 16-bit data.
0003.
Exactly. Yes, correct. 0003. Right? Okay. So this is a simple way of okay, or different models. Tiny models I already told you. Small model. Okay. Now here your data segment and code segment are separate 264 kilobyte of blocks. Okay. In tiny, it will be within 164 kilobytes. Okay. So small is actually which you are using in everyday programming practice. Your data segment is a separate 64K block. Your code segment is also separate 64K block. Okay. So you have medium, okay, where one data segment of 64K byte and any number of code segments for large programs. See, sometimes what happens is your program size becomes more than 64 kilobytes, what you will do during that time? Have you understood this? See, in the lab, you're writing small programs, right? Your program size will not be more than 8 KB, 10 KB, and so on. Suppose when you write a big program, right? So, for example, you take, of course, nowadays it's not a big matter. Some 20 years back, okay, the every systems were using 8386 microprocessor, right? At that time, these higher level programs are not developed. Everybody used to write the program in assembly language. When I have graduated, my first job was to write code for 8086 microprocessor using assembly language, and that is for for the cash registers. And I don't know how many of you seen cash registers, which is widely used in the restaurants and in many of the counters for billing. Those from 20 years to 30 years back, I think it's not, before that there was no computers. People are using this 8086 based systems with the program written in the assembly language, right? In such cases, you see that your data size and your code size will become in terms of 256 KB, 512 KB, more than that. In such cases, you cannot put everything in one segment, right? One 164K block. Okay, definitely one has to use large models. That's why these different models have come, right? So medium model tells you that data will be within one segment, within one data segment of 64K byte, and you can have any number of code segments, right? That means different numbers of segment address for the code for the large programs. Similarly, compact, you can use one code segment program, okay, and any number of data. Sometimes your code size may be small, data size is big. You can use compact. Sometimes data size is small, code size is big. Go for medium. Okay. Now, if everything is everything is high. Suppose your data size is also high and code size is also high. Go for a large model. Okay, go for a large model. Okay. Now, huge. Okay, same as large, but the DSS may contain more than 64 KB each. Okay, this huge is actually model for the different versions of the microprocessor, right? Okay, see this in your lab, since you are using very small programs, you can, even tiny model is also good for you, but okay, so you can use dot model small. But if your program size and data size is big, if it is more than 64 KB, then you may have to go for a medium, compact, and the large model, right? So as a knowledge point of view, you're supposed to know this. Okay, so this is what actually is talking about your different types of models. Okay, tiny model within 64 KB. Okay, and you have small model, right? You can have 64 KB for the data and 64 KB for the codes. Okay, so these are the structures of your program, which you already know. Okay, so dot stack is used to reserve some memory for the stack, right? So dot stack is for the memory size, stack memory. If at all you are using any stack, if at all you are using a string instruction in your program, then you have to use dot stack. Okay, dot stack. So this is the program structure. You already know about it. Now we have seen what is your program structure, right? And very importantly, I want to tell you why this move ax comma add data and move dx comma ax is used. Many of you still doesn't know. After this dot code, why you use this? Why you use this? This is very important. Why use this? Listen carefully. This sentence I'm going to use I'm going to give you now is very, very important to understand what is this. See here, you use dot data and you have some data here. Yes or no? You have some data here. This data is stored in data segment with some segment address. It is stored in some segment address. Right? This is your data. This is your data. This is your data. That is data corresponding to this program. Data which you're going to use here. These are the data used in the program, in the same program. When you want to use the same data in the same program, this program should know, from which data segment its data is stored. Its data is stored. Its data is stored. It is stored in some data segment. Right? So this program need to know which segment is that. That is what you're doing here. You're trying to put the segment address, the data segment address, where this data is stored into AX register. And from AX register, you will load it to DS data segment register. Okay. So if you load the proper segment address into data segment address, microprocessor will look into same segment for the data. That is this one. Right? It will get its data. But if you don't do this, what will happen? Your data segment will have some random value. Whatever data is taken for this particular program is coming from some random data segment, which is not yours, something else. That's why doing this move AX, add data, move DS, AX is mandatory to get your data declared or stored in the memory for your entire program. This is very important to put it in terms of stars. You understood this? Okay, never forget this. What is the purpose of this? The purpose of this. Okay, fine. So next we'll continue our study of instructions. Compare instructions. You must have seen about compare instruction, right? CMP, compare instructions. See, always comparison is very important for a very good programming, because with comparing only you'll be able to take some decision, right? Okay, so we always compare ourselves with others and do some take some decisions and do something in our life. In a similar way, compare instruction is very important instruction in your 8086 microprocessor. Have you understood this? Okay. Okay. Compare instruction. What it does. What it does. What are different ways we can compare data? Compare instruction, it compares the data. Okay. It compares the data from source and the destination. From the source and the destination. Okay. So now, what are the data it will compare? See here. Compare CL within the square bracket BX. What it does? It compares content of the CL. That means it's comparing 8-bit value stored in the CL register with the memory location, whose offset address is in the BX register. So when I say CL, compare CL and BX, this offset address is pointing to a byte only, right? It will compare a byte from CL and also a byte from the memory whose offset address is in the BX. Right? What it will do after comparison? What it will do after comparison? That's very important, right? What it does is, it will affect the flag registers. It will affect the flag registers. What are those flag registers affected? Right? What are those flag registers affected? What are those flag registers affected? Carry flag, zero flag, and sign flag, depending on the value of both destination and source. Right? Now, suppose, let us take an example. Compare CX and BX. It will try to compare the content of CX register and BX register. This is a word. This is also a word. It will compare these two. If CX is equal to BX, what is the result? It will be 0, right? It will be 0. Right. So what should happen to zero flag? Zero flag should raise to 1. Is there any carry? When it will get a carry? If CX is less than BX. If CX is less than BX, it will be this is less than this, right? Then it will generate a borrow. See, actually what it does is, it does the subtraction of CX and BX. It will subtract these two. It will subtract CX and BX. Actually, what compare instruction does, internally it is actually, it subtracts, it makes CX minus BX. Right? Content of CX is subtracted, content of BX is subtracted from CX. If contents are same, if CX is equal to BX, zero flag will become 1, right? Your carry flag will become 0, and sign flag also will become 0. Right? Now, suppose if this number CX is less than BX, when this is smaller, you are subtracting a big number from a small number. Definitely borrow is generated, right? So in that borrow here, in this case, here borrow carry is same. That means if CX is less than BX, carry flag will be 1. Also sign flag will be 1. Why sign flag will be 1? Because result is negative, right? You're subtracting a big number from a small number, right? Definitely result will be negative. That's why the sign flag will become 1, carry flag will become 1. In the case when your CX content is less than BX. Now, when CX is bigger than BX, that means you are subtracting smaller number from the bigger number. No borrow generated. So carry flag 0. Okay. Now, definitely your zero flag is also 0 because numbers are not same. So result is not 0. Similarly, sign flag also 0 because you have a positive number. Have you understood this? Okay. So these are the flag registers which are affecting. Then other flag register, overflow, parity, auxiliary carry, it depends on what type of data you have. But 3 main flag register which are to be used with this compare instruction is this carry flag, zero flag, and sign flag. Right? So quite often we'll use this compare instruction in the program. Right? Okay. This is about compare instruction. Okay. Similarly, we have after compare, right? What to do? Right? After compare, what to do? Right? I say that, okay, my friend is actually taken a car of 1 million. right? Then what I should do, right? I should do something, right? I should do something. That's where your jump instruction comes. So actionable, instruction. This jump instruction also called as control instructions, right? If Cx is less than Bx, do something. The same thing. The compare instruction always followed by jump instruction. In any programming, this compare instruction always followed by jump instruction. What are the jump instruction we have? See, jump on above, jump on not, below, or equal. Jump on above. See, after this jump instruction, you will have label, right? So after jump instruction, you will have a label. See, suppose if I use jump on above, okay, then I have a label here. I have a label here. This label tells you from where it has to start executing. It has to start executing if that condition is met. Okay, jump on above. Jump on above means, suppose you use compare Cx and Bx. Okay, I will use a simple example, compare Cx and Bx. Then I will put jump on above up. Okay, jump on above up. That means up is somewhere I'm assigning here. Suppose some move instruction, move ax, comma, cx, something I have. Okay, don't worry about it. Now, jump on above means if this number is greater than this number. Okay, jump on above. If cx is greater than bx, right? So when cx is greater than bx, jump on above, it will check the carry flag and the zero flag. Carry flag and zero flag. Right? It will check the carry flag and zero flag. If this is satisfied, what is the meaning of satisfying this? What is the meaning of satisfying this? Satisfying this condition means your CF should be 0 and also zero flag should be 0. Jump on above. That means this result is greater than this. It is not equal. It is above. Right? So what will happen is, if Cx is greater than Bx, it will satisfy this. It will go to up. It will go to up. It will start executing from that place. It will jump its execution to this place. Suppose if Cx is less than Bx, what is the condition? It fails, right? It fails. That means your carry flag is 1, right? In such case, it won't satisfy this. It won't go to up. It will start executing from the next instruction. It will start executing from the next instruction. This is jump on above, right? It is same as jump on not, below, or equal, right? It says your Cx, your in this case compare Cx Bx. It says your Cx is not below not below or equal.
What no one expected was this. After taking
Right? Okay. I've understood this. This is what actually compare instruction followed by jump on above. I've understood this. Okay. Similarly, you have many jump on above or equal. Jump on above or equal. See, you normally use this in if A is greater than or equal to B. Same thing. Jump on above or equal. That is JAE. JAE. Now, suppose if I have an instruction, suppose you have, I'll just use compare Bx, comma Cx. If I have jump on above or equal, okay, jump on above or equal, right? Okay, jump on above or equal, I will just give up, and my up is somewhere here. Up is somewhere here. Okay, so what is that condition it is actually doing now? It will satisfy, this is satisfied, it is satisfied when, only when, okay, under two conditions. One condition is that if bx is greater than cx, if bx is greater than cx, and also bx equal to cx. In both the condition, this will be satisfied. In the both the condition, this will be satisfied. Have you understood this now? That is jump on above equal. Right? Whenever carry file is 0, okay. Suppose if bx is in any case, if bx is less than cx, does it satisfy? Does it satisfy this? No. It won't go to up, but it will start executing from the next state. Jump on below. Jump on below. Jump on below. This will be satisfied only when bx is less than cx. Jump on below. Or jump on carry. Jump on not above or equal. Right? Jump on below or equal. Less than equal to. Okay? Jump on not above. Similarly, jump on equal. When 0 flag is equal to 1, jump on 0. Right? Now, if I take the same example, so I'll just use jump on 0. Up. When it will go to up, when next instruction executed is from up, only when your bx is equal to cx, or your subtraction of bx and cx is going to give you 0. Okay, this is the way this jump instruction works. Jump on not equal to, or jump on no 0, right? So depending on this condition, this jump instruction will work. Okay, so all of you must have understood now what is jump instruction. So we'll write the program, then we will actually know everything. Jump on greater, jump on not or less than equal. Okay, jump on greater or equal, jump on not equal. This is the statement used when you use after the arithmetic operations or compare instructions. Okay, so this is normally used after the arithmetic instruction. Jump on greater equal. Okay, so try to know each and every point. Now let us write a program. Okay, let us write a program, because see, all these instructions will be pakka for you once you write the program. All of you take down this program on your notebook, please. Even if you are there online, try to take down this on your notebook. If you really seriously you wanted to learn, get good grades, try to learn programming and try to take down this. I'll give you 2 minutes to write the program. Write the program independently. Write the program independently. Right? Let us not copy from or by heart from whatever is written or whatever is available. Let us not do that. Right? Okay. Write an ALP to find the greatest signed number from a set of 10 bytes stored at a variable called array. The greatest number must be stored at the location res. We are not only finding the greatest number, also it should be stored, okay, in a memory location called as result. How do you write the program for this? Right? You have 10 bytes of data stored in a location called array. How do you write the data part of this? Don't try to get the program from ChatGPT or somewhere else. Try to write it yourself. How to write the program? Okay, dot model, all those things will come as usual. Don't worry. Dot model, small, all those things, blah, blah, blah will come. Don't worry. Now, let us start writing from dot data. Dot data. Right? Okay. So now you can write here array db. Now you can just initialize 10 bytes like 12H, comma 14H, comma 20H, okay, comma 30H. 10 bytes you write like this. Okay, fine. Okay. Now result is also db. Put it as a question mark. Yes or no? Right? So I've understood this. Okay. This is the data part. If you want to put count, we can make it as a variable count. Suppose if you're using loop statement or anything, you can put count as 0, 0, okay, 0, H. 10 bytes, na? 10 bytes. This is the way you can just put it. If you're using loop statement, then it has to be count has to be in the CX register. If you don't use loop statement, if you simply use the put the loop by just decrementing and using jump instruction, this is not required. Understood this? Okay, this is the data part. A small part of your program is done. A small part of the program is done. Okay, right? Okay, can you write that? This is the compare. How do you compare? How do you get the greatest value of the in a set of array? Just think. Have you written any program in C program? Yeah, you have done C programming, right? In C programming, have you done anything like this? How do you have a array of numbers? How do you find the greatest number? Compare, right? Compare first number with next number, right? Then you check whether next number is greater than the first number. If next number is greater than the first number, next number will become greater number. Have understood this? Highest number. So like that, compare every number one by one, okay? And then ultimately last, comparing all the 10 bytes, you get the highest number. You can use that algorithm, right? Okay. Let us start the program. Okay, let us start the program. I told you, first you declare 10 bytes. First you declare 10 bytes. Okay, so how do you declare 10 bytes? I told you, is the way you declare 10 bytes. Okay, see, declare 10 bytes. Is the way you declare 10 bytes. Of course, model tiny is used, no problem, don't worry, whatever it be. Result, that is highest number is stored in a memory location, result. And you all know, see, these are only the memory names. Actually, these are nothing but offset addresses. Okay, So if you put org here, okay, 0000H, it's supposed to start from the offset address 000H. Okay, so what I will do, see, this is an array, right? This is an array. See, whenever you deal with the array, it's offset address. See, this is the offset address now. Suppose 0000 is the offset address, which is pointing to 91, Okay, so we have to tackle the number from here, right? We have to tackle the number from this particular place. That means we need the address of this 91. We need address of this 91. So I will actually use a pointer, okay, BX for this. That means I will put the offset address in a pointer BX, in the BX register. BX register is going to be a pointer, right? So I want this offset address of this 91, okay, to be loaded to BX. So what I use, I told you just now, load effective address. We can use an address, an instruction called as load effective address. Okay, so see what it does. The load effective address of this array is loaded to BX. So BX register is now holding the address of array, It is holding the address of this. That's the address of this 91 actually. Right? So now I'm using the data using my pointer in the BX register, using my offset address in the BX register. Okay. Now, every time I will compare this number with the next number. Okay. Every time I will compare this number with the next number. If this number 91 is greater than 02, okay, I will actually save that highest number in one register. Every time I'm comparing two data, okay, so what I will do, I will keep the highest in one register. I'll keep the highest in one register. Right? Okay, I'll keep the highest in one register. Right. So now what I will do, I will compare 91 and 02. Right? If now this first number is greater than the next number, right, then I will keep that highest number into one register, say AL. Okay, then I will compare this highest with the next number. Okay, like that every time I'm going to compare highest with the all other number. Ultimately, my highest number, then I will update the highest number in that register. Ultimately, after comparing 10 times, I will have that highest number in that particular register. That's why I have to put this inside the loop. Okay, 10 times. I'm putting the loop counter 0A. 0 is nothing but decimal 10. I'm going to put it in the CL register. I'm going to put it in the CL register. This is nothing but your count. This count I'm going to put it in the CL register. Now I will start my work. Okay. Now I'll put the first number. Okay. I'll put the first number 91. Right. Now your BX is pointing to here. I'll put that number from the memory to AL register. Now my 91 is coming to the AL register. Right now AL register is going to be the 91. I will consider this now as my highest number maximum. Right. So now what I will do, I will decrement this count by 1 because I will just try to compare with the next number. Right now increment BX. Why I'm incrementing BX now? See, BX is pointing here now. Now I have to compare. This is the address of this 91. I have to compare this with the next number, which is my address BX plus 1, That's why I'm incrementing the BX here. Now this important instruction you see, compare AL. What is there in AL now? 91. And within the square bracket BX. Right? Data from the memory. I'm comparing a register with the memory content where this is pointing to BX. Now this is actually BX plus 1. Bx I have incremented by 1. Now Bx is pointing here too. It is comparing 91 and 02 now. Okay, it will compare. Now, what it has to do after comparison? What it has to do? Jump on greater or equal. See, if this number is greater, okay, if this number is greater, do I have to change this content? I need not change the content of AL, right? It will remain as AL only. It should remain it should keep the maximum number, right? So that's why I'm putting a example here, one instruction here, jump greater than or equal. What it has to do, if it is greater than or equal, it will jump to X. Can you come here? See here, it will jump to X. What it will do? It will simply increment Bx. It will simply increment Bx. It will simply decrement CL. Right? Now, if the CL is not 0, what is the CL value now? CL value is just 10 or 8. Right? It will check it will decrement CL and it will use jump on no 0 X2. What this jump on no 0 does? It will check whether CL register is 0 or not. CL register is not 0 now. We just begin with now. Since CL register is not 0, it will go to X2. What it will do in X2? It will compare that AL register, which is not changed, still the highest one, with another value, with the 83. Next iteration, this will be 83 and 91. Next iteration, this is 91 and 83. It will do once again compare. Now once again, this is greater or equal. Satisfies. This satisfied, right? 91 is greater than or equal. Okay. Then once again, it will increment Bx. It will increment Bx. Now you see FFH. And then it will increment CL. Okay. Then jump on the no 0 X2. It will try to take next value with the 91. Now, in that case, the next value will be here. FF. This is 91 same. This will be FF. Next iteration 91 FF. Which is the bigger one now? Which is the bigger one? This is the bigger one, right? This is not satisfied. When this is not satisfied, it won't go to X1. What it will do? It will update your AL register with the FF. Now it will update your AL register with FF. Because this is not satisfied. It will not come directly here. It won't come directly here. It will execute the next instruction. It will update the AL register with the highest one. Then it will actually increment Bx, decrement CL, check all the numbers are done, and it will do the next. It will compare FF with the 75. Right? And you can see that for all these data, FF is going to be the highest one. Right? So highest value in this is finally AL will have FF that is stored in the memory location RES. So RES will have FF. Right? This is the way you can write a program for finding the highest value in the set of array. Now see here. Now this decrement CL jump on no 0, right? You can use a loop statement instead of this. How do you use a loop statement instead of this? This is replaced by loop X2. How do you replace the loop X2? Now what you have to do is instead of CL, you have to use 000AH. And then you replace this to the loop X2. What this loop X2 does? This statement will decrement internally CX register by 1. Okay, decrement CS by 1 and check it is 0. So this actually, this is what actually replaced by one loop. Same thing, it does the same thing. It does the same thing. Same, these two statement is replaced by one instruction. This is what the beauty of your CISC instruction set computing. Okay, this is the beauty of CISC instruction set computing. You can replace this with the loop x2. Right? Okay, so this is the way you can write a program to find the largest of the number in a given array. So try to practice this program. This type of program will appear, it will come in your examination. Right? So here, what are the instruction we have studied? We have studied about load effective address, which loads the address of the array into BX register. Right? We have studied increment, decrement, what increment, decrement does. Compare we have seen. Jump on greater or equal we have seen. Right? So these are the instructions we have seen now. Okay, to write a program for finding the highest in an array. Okay, so try to practice this program, practice different type of programs. I'm sure if you are a good programmer, at least good program you can write in microprocessor, you can get better marks. Right? So without doing well in programming, please don't expect good grades in microprocessors. Okay, so simple program, not a big program what we expect you to know. Simple program you need to know, and this is possible only when you don't by heart the program. You just try to practice, try to write your own program. That's right. Okay, fine. Okay, now and instruction. Okay, this is called as logical and instruction. Okay, this is called as logical and instruction. Okay, logical and instruction. Okay, so and destination source. Okay, you know what is logical and see destination source. See, always whenever you have this type of destination and source, what you do is very simple. See, this can be registered. This can be registered. The content of the register. Okay, sometimes this can be register. This can be memory. Right? So sometimes this can be memory, this can be register. But be careful, this memory and this memory is not possible. Okay, only these are the possibilities. Just remember this. Why it is source, destination, and all is coming here. It's doing AND operation. Okay, what is something we are going to get from AND operation? Your flag register. Right? Similarly here, mainly here you actually will have a parity affected, sign flag is affected, zero flag is affected due to the AND operation. Right? I understood this. Okay. So now AND operation, what will do? It just the AND operation. I think I did not tell you much about AND operation. You know about it, right? Okay. See, suppose your AX register consists of I will take AL. Okay, I will take AND AL, comma BL. Okay. So what it does? So AL register is content is F. BL register is say F0. What is the operation of the? What is the result of the AND operation? What is the result of AND operation? Where it went? Yeah. What is the result of AND operation? F0. AND it. How do you AND it? Tell me, how do you AND it? Simple. See, 1 1 1 1 1 1 1 1 1 1 1 1. Okay. 0 0 0 0. F0. So it is 1 1 1 1 0 0 0 0. Okay. This is the way you can do the AND operations. Okay. Okay, we will enter the class in another 5-10 minutes. Okay, so I just want to complete this AND operation, not operation. What it does? Not of operation, right? It will complement every bits. Suppose AL register in this case, having the content say AB. What is the NOT operation of this? What is A? A is A1010, right? B is 1011, right? Now, what is the NOT of this? 0101 0100. This is the NOT operation. That's it. What about this? I told you it will do a NOT of the content of the memory. It will do NOT operation only on the byte, not on the word. Okay. So if it is word, it will do it on the 16-bit data of this in this offset address. Okay. Try to know all these things. This is very important. NOT operation, negative. It does 2's complement. You know what is 2's complement? You know, 1's complement plus 1. Right? Suppose if we give negative of AL, if AL is having some data, okay, it will find the 2's complement of the data. Okay, just you need to know about this. String instruction. So before coming to the string instruction, I want to tell you about rotate instruction. This is very important. I want to tell you about rotate instruction. What is rotate instruction? It is very important for you. Okay. See, rotate. You may have to rotate the content of the registers. Right. Rotate content of the registers. See, what is rotate and shift? This is something you already know. See, why I am actually telling you this in the last moment of this class, because you already know about it. Okay. See, what is rotate and shift? See, this is your AX register. Okay. And this is your AL register. This is your AH register. Okay. And you have 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7, 8, 8 bit. This is 8 bit. This is also 8 bit. Okay. So now suppose I will take this rotate left. Okay. Rotate left. Okay. So rotate, I will take rotate left AL register by 1. Okay. Rotate left AL register by 1. I will take this AL register now. This is your AL register. 1, 2, 3, 4, 5, 6, 7, 8. Right? So now this is your D0, D1, D2, D3, D4, D5, D6, D7. Right? So what it will do? It will rotate the content of this register AL left by 1 position. Left by 1 position. Okay. So left means what? Tell me. This will come. Sorry, left means it is. This will come here. Rotate left. Rotate left. Your left. Rotate your left. That means D7 will come here. Right? D7 will come here. D0 will come here. D1, D2, D3, D4, D5, D6 will come here. Rotate left. This is rotate left. Rotate left by 1. Suppose if you want to rotate this by 4 times, if you want to rotate this by 4 times, you cannot write 4 here. You cannot do this. Instead of that, you move the count in the CL register. Move the count in the CL register, and then mention that CL register mention the CL register here. Always do this. What this will do? This will rotate this content 4 times to the left. Sorry, rotate 4 times to the left. Exactly. Then tell me, what will be the final content of this register? Where D0 will come? Where D0 will come? Tell me. Rotate where your D7 will come. D7 will come here, right? After sorting 4 times. Then D6 will come. Then D5. Then D4 will come here. Then D0, D1, D2, D3. So this is what your content of the register AL. Content of the register AL. Okay. After rotating left. After rotating left, how many times? 4 times. Similarly, you have rotate right. Same thing does in a reverse way. Rotate right. Similarly, rotate right. Okay. See, this is an example. What happens to the rotate? One by one, you can check what's happening. Now, same time, one very important thing you see, every time it rotates, okay, to the left or right, while rotating left, its most significant bit will go to the carry flag. Okay, that you have to remember. Similarly, when it is rotating right, its least significant bit will go to the carry flag, and then it will go to the, then it will rotate. See, this is, you can see this is rotate right AX1. See what happens. See how it is rotating once. See, content is, the content is, see the content is FF00. Okay, 16-bit content. Okay, rotate AX, rotate it actually 4 times. See, instruction is move CL, 04, rotate right AX CL times. See, first rotate, what is going to happen? See, can you see first rotate what happened? The least significant bit also is going to the CF. Second rotate, see, second times. Third time. Fourth time. It's rotated 4 times now. What is the content of the AX register? Your FF00 become 0FF0. Okay, this is rotate right. Okay. Similarly, rotate left. Rotate left. See, 4 times. See what happens. See, 4 times. Okay. Now, see what is the difference between rotate and rotate with carry? Rotate with carry. So what happens during rotate with carry? See, earlier what was happening? Earlier what was happening? See, this was happening earlier, right? Okay. See, every time what happens is, it is rotating within this. It is rotating within the register. But every time while rotating left, if your most significant bit will go to the carry flag. But this is going to the least significant bit, right? Now, in RCL, what will happen is, in RCL, rotate with carry, this is called rotate with carry. In rotate with carry, what happens is, instead of this is going here, this will go here, and this carry flag will go to the least significant bit. This is rotate with carry, RCL, rotate with carry, right? So the rotation is actually along with the carry flag, right? Similarly, rotate actually left, right? This is rotate left. Similarly, rotate right. While rotating right, what will happen? This will go here, and this will come here. Rotating right with carry. That is rotating right with carry. Okay, this is not the case of ROL. Rotate will simply rotate within this. Okay, but every time, okay, while doing rotating right, this will go to the carry flag. And rotate left, this will go to the carry. carry flag. Okay, so try to know the difference between ROL and RCL, which is very, very important. Okay. See RCL, what happens RCL? Okay, suppose if you want to swap the nibbles of a data, you can do it over here. Okay. See, how do you swap the nibbles? We will see the shift instruction in our regular class next week. So try to remember whatever is studied here.